Okay. What is wrong with it? Hey. Oh my God. Some or it will be the video will be stopped. Okay? I don't know what happened. So also piece of no. Hello, hello. Hello, hello. Okay, it works. Okay. Hey, 1 and 3 sum up to 1. 3 and 1 sum up to 1. 2, 2 sum up to 1. So there are three elements in the set A, in the event A, or you can say event A. Okay. Okay, A is called an event, which an event is a subset of the sample space. So the probability of A is defined as, hey, 1 over 36, 1 over 36, 1 over 36. So it is 3 over 36. Okay, what is 3? 3 is the number of elements in A. And at 36 is number of elements in A's. So for short, the abbreviation is hashtag. Hashtag, okay, of A. Hashtag of S, of A's, which is the number of A and number of A's. So A is the event that two dice sum up to 4. Okay. So that's the classical probability to calculate the probability of event A. All right. Okay. So for any event in A sample space A, we have the probability of A lies between 0 and 1. Okay. And 0 and 1 are included. Okay. And the probability rule, please go to page 199. Rule number 1, the probability of any event E is a number, okay, between and including 0 and 1. And this is denoted by 0 less than or equal to PE, and PE is less or equal to 1. Okay, that's the rule number 1. And rule number 2, the sum of the probability of all possible outcome in a sample space is 1. They have to sum up to 1. Can we why don't we define the probability between 0 and 2? Of course you can do it, but it does not, it's weird. It's a weird definition. Okay, 0 and 1 is, sounds more reasonable. Okay? And rule number 3, if an event B cannot occur, that is, there is no element in a sample space corresponding to E, then its probability is 0, denoted by P of E equals 0. Okay. For example, the event if E is the event that two dice sum up to 13. Is it possible? Not possible. The maximum sum is 12. There is no way they sum up to 13. So if E is the event that two dice sum up to 13, then probability of E is 0. Okay? Hey, I have to add the right parenthesis here. And where E equal an empty set. Okay? An empty set. All right? And rule number 4, if an event E is certain means surely happen, okay? Then the probability of E is 1. That is P of E equal 1. For example, hey, 2 dice sum up to at least 2. The event that two dice have sum at least 2. That's a surely happen thing. Okay? It surely happened. All right? Why? Look at this. Look at the sample space. This event will surely happen. Why? Because the sum of 2 dice is at least 2. So it surely happened. So the probability of a surely happen event is 1. Okay? Okay. The corresponding event of E is the the complementary event of E is the set of outcomes that are not included in E, and it is denoted as E complement. Hey, please read this. E complement. Okay. So, for example, if E is this event, the event that 2 dice sum up to 4, then the E complement is this: 1 1 1 2 1 4 1 5 1 6. Hey, 1 3 not included in this row, and 3 1 2 1 2 3. Hey, 2 2 not included in this row because anything in the set should not be in the set E. Okay. And what is the third row? 3 2 3 1. And what happened to 3 1? 3 2 3 3. And what happened to 3 1? 3 1 is here. Okay. When 3 1 is here, it should not be in the complement of E. Okay. So how many element? How many element? There are 33 element in E complement, and the event that an E complement is the event that 2 dice have sum. Oh, not there is no E here. Have sum 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. Hey, there is no 4 here. You see that? There is no 4 here. Okay? And there's I have to make a correction. Yep. And hey, So what is the probability of E complement? E complement, hey, defined by the classical probability, it is the number of E complement divided by the number of element in the sample space. Okay, which is 33 divided by 36. But 33 divided by 36 is the result of 1 minus 3 divided by 36. So what is this probability? This probability is 1 minus E, probability of E. So for any event, E, the complement of E has probability 1 minus probability of E. All right? You can say this is the rule number 5. You can say this is rule number 5. Okay? You can call this rule 5. PE complement equal PE. Work again. Hey, empirical probability and classical probability have different ways to define probability. Okay, so now this is a quite different way from classical probability. Okay, example. To introduce empirical probability, the best way is to use the example of flipping a coin. You know, flipping a coin. I don't have a coin. Hey, consider the experiment of flipping a coin and observe whether the head or the tail, 正反面, okay, appears. When you flip it, either head or tail appear. Okay? The empirical probability of getting a head from flipping a coin, hey, it is not defined 1/2 this time. 1/2, hey, what is the probability 1/2? It is the classical probability. Okay? Classical probability, because there are two possible outcomes. And the head is one of them. Head, tail are two of them. And they are equally likely to occur. So it is 1 over 2 and then 1 over 2. Understand? But in empirical probability, we don't define the probability of getting a head is 1 over 2. No, we don't define it this way. And what is the empirical probability? To define the probability of getting a head. Okay. The probability of getting a head from flipping a coin is defined as follows. Do the experiment of a flipping coin for n times. Hey, this time n should be large. As large as possible, say 10,000 or 100,000 or even a million times, okay? And record number of occurrence of getting the head. The number of times the head appears in n trial. Okay? And suppose the head, and next, suppose that the head appears number of h times in n trials of a flipping coin. Then define probability of a head equal to number of h divided by n. For example, you do the experiment of flipping a coin for how many times? For 1 million times. And how many times the head occurs in a 1 million experiment? Suppose that you see how many times? 5,000 of 4,099 of 499,000 and 987 times the coin has head, appear head, and so the probability is defined by 4,999,87 divided by 1 million times you flip the coin. Okay, so the probability is 0.59987. Understand? So to generalize, for any event A is defined using the method of empirical probability. It is defined as PA equal, limit n goes to infinity, and number of times A occur in an experiment, and the number of event A occur divided by the number of experiment you do. Okay, so where hashtag of A is the number of times A occurs in n trials. So this time number of A is 4,999,87. So the probability is defined as this. So what is the difference between classical probability and empirical probability? The classical probability is also called the God's probability, G-O-D, God's probability. Okay? And what is empirical probability? Empirical probability is a seeing is believing probability. 眼见为凭啊. Okay? They are different. Okay, 10-minute break. Hi. Hello, hello. Hey. Hey, time. Time, please get back. Hi. Hey, please look at this. I add a comment to the empirical probability. You can call the empirical probability is seeing, quote, seeing is believing, unquote, probability. But what is classical probability? The classical probability is called God's probability. Okay, God's probability. All right. Okay. Please go to please go to page of the section 4-2. The addition rule, rules for probability, and addition rule number 1. When two events A and B are mutually exclusive. Hey, what is the hey, time, hey, silence, 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 hey. When two events A and B are mutually exclusive, which means that A and B have nothing in common. Okay? There is no element which is both in A and in B. Okay? And not this one. I will correct. You can say disjoint. Okay? A and B disjoint. Or you can say A intersection B is nothing. Is an empty set. Okay. So when they are disjoint or when they are mutually exclusive, then the probability that A or B will occur is denoted as P of A union B is the you can is given by the sum of PA and PB. Okay, that's the additional rule number 1. Hey, only when this equality holds, only when A and B are mutually exclusive. They have nothing in common, or the intersection of A and B is empty. Or you can say A and B are disjoint. Okay? So rule number 2. If A and B are not mutually exclusive, then the probability that A or B will occur is given by PA plus PB minus the probability of A intersection B. Okay? See the example there in section 4-2 yourself. We don't have too much time to discuss in detail. Hey, you can use the diagram to understand the formula. The diagram here. This is A and this is B. Okay? Here it is. The green part is A union B. Okay? And this part is A. This part is A. and this part is B. Okay? So what is the part of the figure that counted twice? Hey, this part overlap. Okay, A and B, this is where O, A and B overlap. And this part, it is included twice. So we have to minus the probability of A intersection B. Understand? So this part counted twice, okay? And this is B. And this part is A intersection B. Included twice. Okay? Included twice. So we have to, that is why we have to minus the probability of A intersection B. Okay? Here. And today we're going to look at the next section, 4-3. Hey, the multiplication rules and the conditional probability. Okay? And let H denoted that the head of a coin appear. Okay? This is H stands for head, and tail stands for okay, and T stands for tail. And for example, consider the experiment of flipping 3 coins. Hey, this time 1, 2, 3, 3 coins. Okay, flip 3 coins. And the sample space is okay, omega, head, 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 tail, head, tail, head, tail, head, head, and all the way to tail, tail, tail. So how many possible outcomes are there in the experiment of flipping 3 coins? There are 8 possible outcomes. Understand? 8. And let the event A, that is A be the event that the first coin is H. Hey, A is the event that the first coin is H, and B is the event that the second, the first, the second and the third, the second and the third are both tail. Are both tail, okay? Both tail? Yeah, are both tail. So, hey, look at again. Look at then again. A is the event that the first coin is H, is the head. B is the event that the second and the third is tail, are both tail, okay? So what is A? What is A? So define the conditional probability. Conditional probability. Okay. Hey, today we are going to look at the definition of conditional probability. Hey, the probability of a event A occur under some condition. Okay. The probability that B occur, given that the event A already occurs. Okay. Okay, this is the conditional probability. All right. Suppose that the event you are given that event A occur, and what is the probability that B occur given the event A occur? So let's look at the set A and B. A is the event that first coin is head, 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 and no more. Okay, that's all elements of A. And B is the event that the tail, the third, and the second coin are both tail, 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 tail. Okay, so what is the intersection of A and B? Intersection of A and B is HTT. Okay, so let us calculate. Let us calculate the probability of B given the condition that A occur. So when you are given the condition that A already occurred, hey, now when you are given the condition, the sample space shrink to A. It's important. When you're given a condition, when you are given a condition, your sample space is smaller. Okay? Shrink to A. I suppose that you graduate and work for a few years, and you want to choose a husband, and then you say, "Oh, my husband should be a PhD." You know PhD, Doctor of Philosophy, 博士啊 doctor, or a medical doctor. Okay, medical doctor. Oh, my husband should be a medical doctor. Then your sample space will be very, very small. Understand? If you're given even more one condition, oh, my husband should be a doctor and handsome, the sample space is even smaller. And you say, if you add one more condition, oh, my husband should be a doctor, handsome, and honest. Oh, the sample space is even smaller. Okay, what I wanted to say is when you are restricted to a given condition, the sample space is limited to the condition you were given. Understand? So the sample space shrinks to A. Hey, the probability that B occur given the condition that A occurs. So now the sample space is A, and it is not ace anymore. Not omega or ace anymore. This time the sample space becomes A. And A already occurred. And B also occurred. So the event, the upper part of the event should be A intersection B, because you were given A occur. Okay? And when you calculate the probability of B, hey, this part should be A intersection B, because you were given that A already occurred. And you are calculating, you are defining the probability of B. So this part, this term should be A intersection B. The number of A intersection B divided by the number of A, which is now the sample space. Okay? Because you were given the condition A. So this time the sample space is A. Okay, so That's the conditional probability. Now, this time, the sample space is no more. No more omega. Okay? And the sample space shrink to A. Hey, it's going to appear in your midterm. All right? So, okay, so what is the probability? The probability is 1 over 4. All right? 1 divided by the number of A, which is 4. So it is 1 over 4. And what is the probability of B? Okay, not given the event A occur. Hey, the probability of B alone. Hey, what is the probability? The probability of B occurs itself and not given the event A occur. It is, hey, this time you were not given the condition. So this time the sample space is omega. Is omega. Okay? Okay. So the probability of B is a 1 over 4. Hey, see what we have. So what is the big deal about the two probability? Hey, the first probability is the conditional probability. The probability of B given that A already occurred. Okay, given a condition. And the probability is 1 over 4. And this time, the probability of B alone itself, not given the condition that A already occurred, is also 1 over 4. Hey, here we see this. Hey, the probability of B given that A already occurred is 1 over 4. And it is equal to the probability of B itself. So what we see here is that given or not given that the event A occurs, the probability of B in the two situations are the same. This is a very special case. The special case does not occur all the time. This time the situation is there are two situations. Situation 1, you were given that A already occurred. Situation 2, you were not given the condition that event A occurred. In the two situations, the probability of B are the same. So what is the big deal? This means that in this case, we call A and B are independent. Hey, the event A does not influence the probability of B, given or not given. the probability of B are the same. So in this case, we call A does not influence B. So we call A and B are independent. Understand? So we can define the independence of two events, A and B, by the following definition. We have three ways we can define the independence of two events, A and B, by 1 to 3 equivalent ways. Okay? Definition, the first method. The first, we have three different but equivalent methods to define the independence of events A and B. Hey, first method is that you can check if these occur. If you can check the equality, the first equality, hey, you can see if given or not given the condition of A, okay, whether the probability of B in two situations are the same. If you were given the probability the condition that A already occurred, the probability of B is the same, not given the condition A. Okay, in this case, A and B are independent. And conversely, you can also given the condition that B already occurred and see if the probability of A is equal to the probability of A itself. Okay, if they are the same, they have the same probability under two different situations, given or not given, given B or not given B. Okay, then you can also say, oh, A and B are independent. Okay, but if you use this definition, you have to suppose that A probability of A is positive. In this case, you have to suppose that the probability of B is positive. Okay, so we have two different ways to see if A and B are independent. Okay. 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 Let's go. Let's go to the here. Yep. Here. Hey, note that. Note that. Probability of A given the probability of B given that the event A occur. Given the condition that event A occur, hey, is defined as number of A under number of A intersection B. Hey, let us divide both terms by number of A's. Hey, the upper term divided by the number of A's. And the lower term also divided by the number of A's. And the result remains the same. Okay? But if you divide this by number of A's, then it is the probability of A. And if you divide the upper part by the number of A's, it is the probability of A intersection B. Okay? So, hey, so if they are the same, then the probability of A intersection B should be equal to PA times PB. Understand? So here we have the third way to define independence. The third way. Okay. The third way. We have three ways to check if A and B are are independent. So definition of independence can be reformulated as, hey, definition, okay, if the probability of A intersection B, E is equal to PA times PB, then the event A and B are independent, okay? So the following three equalities, they are equivalent. To check if A and B are independent. They look different, but they are equivalent. Understand? Equivalent. They are equivalent ways. Equivalent. So when I ask, hello, 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 hello. Next page. So now, is there any example that two events are not independent? Not independent. The next example is the example that to demonstrate that two events are not independent. Okay, and back to the example of flipping 3 coins, and let C be the event that first and the second coins appear at least. Okay, appear at least one head. So the first and the second have at least one head. So what are the element of B of C? First and half at least one head, at least one head, at least one head. Understand? At least one head. At least one head. At least one head. How many elements are there in C? 7. There are 7 elements. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Hey? Do I miss anything? Hey? At least one head. Oh. I think I forgot something. I missed something. First and second. first and second. Oh, there are only 6. Sorry, there are only 6. Only 6. Yep. This one not included. So we have only 6 elements in C. So, and what is the intersection of C? Intersection of C is, hey, intersection of C is HHH, HTT, HHT, and HTH. All right? And what is the probability of C given that event A occur? So it is probability of A intersection C divided by the probability of A. So what is it? It is, no, this time it is. Yeah, it is it. And this is, it is not 7, it is 6. Sorry. It is 6, okay? Yep. So, hey, in this example, we see that if you were given the condition that A occur, then the probability of C is 1. But if you were not given the condition, the probability of C alone itself is 6/8. So they are different. A and C are not independent. The probability of C is higher when given that A occur. So A has influence on C. So they are not independent. Hi. You can call independent. You can call them dependent. Okay? Yep. Understand? In the midterm exam, you will see the example of flipping 3 coins, and I will give you 2 events, A and B, and you have to check whether A and B are independent or not. Understand? What you have to use is any one of the 3 methods. What you can use to see if A and B are independent. What you can use are any one of this. Any one of this, okay? There are equivalent ways. You can just choose one. You can just choose one of them to check, okay? Understand? So please go to example 4-34. It is probably to appear in the midterm. Please go to this example. What is the example? What is the story? Hey, what is the story of the example? Hey, there are 100 persons randomly selected, okay, to survey, okay? 100 persons, 100 people are randomly selected, okay, to undertake a survey. And they are asked whether or not they agree to send woman soldier, female soldier to the battlefield in the war, okay? You see, Israel is now having a war with, how do you say, Palestinian, right? You see female soldier on TV? Yes, I saw it. Female. And Ukraine, also female soldier. And 100 people were surveyed, randomly selected and surveyed, and they were asked a question. Hey, do you agree to send female soldier to the battlefield? And 50 men, in 50 men, 32 say yes, and 18 say, oh no. And 50 women says, eight of them say yes, send women to the battlefield. And 42 says, oh no, do not send them to the battlefield. Okay, the war is too brutal, too terrible. Okay, so what is the probability of what is the conditional probability? If you were given, the probability that a woman will say yes. So it is, hey, it is the number of persons that are women and says yes. How many? 8 of them. 8 divided by 50 because there are 50 women. Understand? So it is 8 divided by 50. Understand? But if you divide it by 100 and so is this divided by 100, then it is the probability of yes intersection F divided by the probability of F. Okay? So you calculate, you finish the result. So is this. You finish the result. I'm not calculating it for you because our time is so limited. And this one, I think we have no more time to go further. So that's for the week. And roll call time.